All right, welcome to Earth Science, everybody. Let's talk about this big scary word, uniformitarianism. But don't panic, it's actually a fairly straightforward principle that we need as another tool for figuring out what's gone on in Earth's history. Now, we've talked about relative dating, where like the older things are on bottom, the younger things are on top, and all that cross cutting and all that stuff. We still have to talk about absolute aging, like radioactive decay. I'm waiting for some supplies to come in before we finish that lesson. So this really isn't our last new lesson here. But uniformitarianism, how does that help out? What it says is that basically, if you're a good earth science student, if you figured this stuff out, then you kind of know what clues to look for in rock from the past. All right. So in other words, if we really go, here's the shorthand for what uniformitarianism tells us. It says that the present is the key to understanding past. That if we go and we study our earth science and we understand present day natural processes, like the way that rivers erode and deposit sediments, then we can see how those same processes work throughout Earth's history. There's no reason why rivers would have behaved differently before humans evolved. The way that they work is governed by the basic laws of physics here in this universe. That's consistent, whether we're watching it or not. So now that we've watched it for years and thousands of scientists have put in millions of hours of work of understanding how rivers work, if we can see that in the rock record, we know what was going on in the past. I know I've said this about sandstone. If you find sandstone that's made from sand, where on Earth today do you see sand accumulate? And therefore, what environments would be like would sandstone come from? You know what I'm saying? It's understanding Earth's history by understanding how things work today. All right. So we're going to need that rule when we get down to this. Let's put it all together. And again, it's not going to be our last lesson this year. We have to go slightly different order here at the end. Let's think about where we've been here in Earth science, though. Our universe began about 14 billion years ago. Who remembers the name of that? I can't really ask you because you're watching it on YouTube. That was the Big Bang. Bonus points if you remember the evidence we had for that: cosmic background radiation and redshift. Our planet and solar system, so that like made the whole universe 14 billion years ago. Our planet and solar system formed out of a nebula about 4.6 billion years ago. Over here on the left, I've got just this is the far skinny little column from that great big page 8 and 9 of your reference table. But if you ever forget this 4.6 billion, it's right here. 4,600 million years is when the planet formed, and then a very long Precambrian, followed by just these little tiny bits of Paleozoic, like ancient life, Mesozoic, dinosaurs, and Cenozoic, where humans would arise at the very, very, very end of. All right, so let's think about this very early planet. I always say that the early planet, and I apologize if you're not a Star Wars person, but early planet is like the Mustafar system planets. Should I pull that up so that our non-Star Wars folks, there we go. So not very hospitable, um, very thin crust, lava, constant bombardments by meteorites still happening. Not a very easy place to live at all. There was no life at that point. So besides all of that chaos happening, and eventually the planet would cool and the crust would get thicker, and the amount of bombardment by meteorites would slow down because we ran out of them. But we're still missing two really important things that we humans are quite fond of. We don't have yet. We haven't talked about how we formed an atmosphere. Onto that. It's keeping us all alive right now. And like water, oceans, water. I don't know what you're referencing, but what I should say is just the hydrosphere. All right, so where did these come from? Well, let's use uniformitarianism. If you go to a volcano today, we can see what gases are coming out. And the inside of the planet, as big as it is, that's been pretty consistent. there's no reason to assume why the gases in the past coming out would be any difference. So the big ones that we're going to need, I mean, I got a list right here of some of them, some other ones, but the big ones we're going to need, and of course there's lava, magma coming out. But what gases are coming out? We've got CO2, carbon dioxide. There would also be some carbon monoxide, CO, less important though. There would be H2O, water. There would be methane. I'll write that because I don't know if everybody's going to recognize methane gas. Is it on my list over here? Ammonia, nitrogen, um, CH4 for methane. Um, we don't need to do all those. Don't worry about it. But the big one being that okay, carbon dioxide's coming out and water's coming out. What's missing though? What's not on that list that we're quite fond of as humans? We don't have any oxygen yet. So our primitive atmosphere did not have oxygen at all, just those gases that come out of volcanoes would be stuck to the earth because of gravity, and would those volcanoes just pumped and pumped and pumped and pumped and built up this primitive atmosphere. So now we got to get oxygen somewhere to get to today, right? And these levels, again, through the rock record, are all detectable, testable, traceable. Um, but we got to a point where these funny little mushroom shaped colonies of single celled organism called stromatolites. I'll do some pictures of too because I don't think those drawings are going to do it justice. But these kind of like mushroom shaped rocks, and the surface is like a live layer of single celled organisms called cyanobacteria, um, which we should write in here. Single celled organisms that lived in warm, shallow seas called cyanobacteria. All right, cyan being a color kind of blue green, right? And they built up these colonies called stromatolites, like layer by layer by layer by layer. Well, these fellas, these single celled organisms, their trick was that they figured out, not figured out like consciously, but they evolved photosynthesis. And if you remember your photosynthesis from last year with Mr. Hefty, that'd be carbon dioxide coming in and oxygen going out as a waste product. So these guys managed to take CO2 in as their respiration, like the same way a tree does today. Photosynthesis has kind of stayed the same. And they got this nasty waste product of free oxygen out there, which would fill the oceans and then eventually fill the atmosphere. You got to learn some chemistry to figure that out, but it's a thing. O2. All right. Oxygen, it's actually, ironically, it's yes, it's we need it. It's keeping us alive right now. But if you've ever heard of eating foods high in antioxidants like fruits, um, oxygen is actually some pretty nasty stuff. In fact, this organism filled it with so much oxygen that it was very bad for this organism. They believe it or not, a species on Earth altered the atmosphere so severely that it was bad for them. And this species on Earth was a single-celled organism that did this. Oxygen's nasty stuff. Like, um, if you're on oxygen, they really try to control it. My little dude here was in the NICU for a while, and they had him on oxygen, but they only would crank it up to like 25%. Regular air, which you can get from the bottom of your reference tables right here, is about 21% oxygen. So that was only a little bit more because oxygen is kind of nasty stuff. Eat your antioxidants so that you don't that doesn't damage your cells so much. Ironic because we need it, right? But these single-celled organisms managed to fill the whole entire atmosphere with enough oxygen to change it. Some of them did, like some strains of these guys did survive. They still exist today, but it was bad for them as a whole. However, filling the atmosphere with oxygen also opened the door for modern life as we know it. So what's the lesson here? And part of what I want to do a little bit more, I want to talk about how humans have done this. A living organism on Earth has changed the composition of the atmosphere. And this was a single-celled organism just doing photosynthesis in shallow seas. Could this happen again then? Yes. Like maybe people are doing it. So the most important lesson of all of this stuff that we've been doing for a year now. We live on a dynamic planet. Pay attention to it. So we are going to think about that a little bit more. I got basically 2 lessons left, I think, and we're all done. We're going to talk about how have humans done this kind of same thing? How have we altered the nature of the atmosphere through human activity? And then we've still got to do the radioactive dating thing when my supplies show up. So here's 5 quick questions on what we just did. I think the first 3 are pretty straightforward. This one, you'll need the reference table, but you can steal it from this little skinny guy right here. And same with that one. 5 questions, very doable. All right. Thanks a lot, folks. 2 to go. Keep it up. We're almost there.